Hello, welcome to my Math 241 trigonometry factors. And today we will cover section 1.3, section 1.4, and section 1.5. However, please keep in mind that before you watch this, in the previous lesson, in lesson 2, I covered section 2.3, 2.4, as I remember, right? Okay, and make sure you watch the supplemental lecture video first before you continue with this. And after you watch this, 1.3, 1.4, and 1.5, then the next thing you watch is the supplemental lecture videos for these sections. Okay, now section 1.3, let's start. This is the first definition of definition 1. Trig functions on coordinate system. Coordinate system. I know it could be a bit confusing, but in section 2.1, actually we did definition 2 first. Okay, let's review a little bit. Recall that in section 2.1, we have definition 2. So our textbook start with definition 1 and then go on with definition 2. The way I think is I rather start from definition 2, which is trig functions on right triangle. Okay, let's review a little bit what it says. It says the following. Suppose we have a right triangle ABC. Right angle at C. Of course, the following naming still applies to actually all math classes. The opposite side of angle A is lowercase a. Opposite side of angle B is lowercase b. Opposite side of angle C is lowercase c. Okay, that's the naming. Now, then for angle A, sine A is defined to be the opposite side over the hypotenuse. Cosine A is the adjacent of angle A, which is side B, over hypotenuse, and tangent A is the opposite side over the adjacent. Now, that's for the primary trig functions, right? Okay, now, and then the secondary one, secant A, which is the reciprocal of cosine, is hypotenuse over adjacent. Cosecant A is hypotenuse over opposite, and then cotangent A is the reciprocal of tangent, which is the adjacent over opposite. Okay, now this is the trig functions. I think it is still the easier way to understand trigonometry if we start from right triangle. Okay, now why? Because we get used to right triangle, and the angles in the right triangle beside this right angle here, we are dealing with an acute angle. Either angle A or angle B here are acute angles, right? Now, the weakness is that then because the angle A and angle B are only acute angles, then we can apply these trig functions only on angles less than 90 degrees. Okay, now definition 1 actually extends that definition, extends the idea of trigonometry. Instead of only acute angles, we extended to more than 90 degrees situation. Okay, so that's the weakness of definition 2. Now we go back to what we need to do here, definition 1. Now you will see this definition 1 is not different from the trig functions on the right triangle. In some sense, it is actually extending the idea that we learned from definition 2. We start with the following. Let theta be in standard position. In section 1.2, we learned what is angle in standard position, right? Okay. And coordinate xy is on any point. Maybe I should say is on the terminal side. Let's picture what is this first. Let's picture what we are talking about here. So suppose we have a coordinate system, okay, and then we have angle theta in standard position. Let's say this is angle theta here, okay. X comma y is on that terminal side, okay. So the x component is adjacent, okay, and the y component is the opposite side, okay. Now, and then the radius is the distance from origin to that coordinate. We call that r. In some sense, you can mimic that we actually have a right triangle here. Right? This is our right triangle. Okay. Now then, sine theta is defined to be y over r. Now, if you see this yellow triangle here, the yellow right triangle here, it is actually coincide with the definition of trig functions in right triangle, where sine theta is opposite over hypotenuse, right? Okay. Now, when we superimpose this angle on coordinate system, instead of seeing that from a right triangle point of view, we put this on a coordinate system in standard position, okay? Then sine theta will be the y component of that coordinate, actually any coordinate on the terminal side, divided by the radius, which is the distance from origin to that point. Now, cosine theta, similarly, will be the adjacent of that theta. In this case, is the x over r, and tangent theta will be the y over x. Now, that's for the primary trig functions. For the secondary one, similarly, secant theta will be r over x. Cosecant theta will be r over y, the reciprocal sign, right? And then cotangent theta is x over y. Now, so far, the idea actually still very similar to what we learned in section 2.1. Okay, what is the difference? The difference right now is that it doesn't have to be seen from a right triangle point of view. We can now see this from a coordinate system. In other words, later on, then the x and the y may be negative. Okay, depends on where the terminal sides located. It doesn't have to be in quadrant 1 like in this picture. Maybe in quadrant 2. So let's say we have this instead. Okay, and then let's say this is our coordinate x comma y. Now the angle in standard position, the theta angle in standard position is this one here. which is more than 90 degrees, right? Okay, now then the sine of this angle theta, even though theta is in quadrant 2, the sine will be the value of y divided by the radius, the distance from origin to that coordinate, and so on and so forth. Okay, now next, let's do an example for that. Suppose, for example, let the coordinate -3, 4 be on the terminal side of theta. Since I don't say anything about what is angle theta, then we assume by default that's in standard position. Okay, now -3, 4, let's say approximates here. This is -3, 4, which is in quadrant 2. Okay, now then we can answer this question now. What is the sine of this theta? Okay, notice that the x is equal to -3, the y is 4, then what is the radius? Well, by Pythagorean theorem, x squared plus y squared equals to r squared. Boom, you will see r equals to 5. Right? Now then, sine theta will be the y over the r. Cosine theta is the x over r. Tangent theta is the y over r. Oops, the y is 4. I'm sorry, y over x. What am I doing? Y over x. Okay, and as for the secondary trig functions, secant theta is the reciprocal of cosine, -5 over 3, cosecant theta, reciprocal of sine, that's 5 over 4, and cotangent theta, which is reciprocal of tangent, is -3, 4. Okay, just that simple. Just that simple. Now, so if we know a coordinate on the terminal side, we can use that coordinate to find the trig functions of the value of the trig functions. Okay. Now, suppose on the other hand, what we know is the angle. Let's say, for example, let theta be 45 degrees. Now we already know the trig values of 45 degrees from section 2.1, right? Okay, but let's confirm that even if we compute using this this first definition here, we will still get the same result. So we know 45 degrees is in the first quadrant, right? Actually, that's a line with slope 1 passing through the origin, right? Now, then what you will do is you choose any coordinates on this line. Any coordinates, seriously, any coordinates. The easiest one, of course, 1, 1, right? 1, 1. But you can also choose, for example, 2, 2, any coordinates, as long as it's not the origin. Okay, let's decide to use 2, 2 instead. Okay, so the x equals to 2, the y equals to 2. We compute. So the angle is 45 degrees. I think I need to say it again. Now you choose a coordinate on the terminal sides. Now make sure that coordinate is on that terminal side. Okay, now once we get that coordinate, let's say we use 2, 2, you will find out using Pythagorean theorem that the r equals to 2 radical 2. Now then, the sine of 45 degrees will be the y over r. Notice that the two cancels, right? Okay, and if we rationalize, we get radical 2 over 2. Now, likewise, cosine 45 degrees, we have exactly the same thing, right? But this time it's the x. Maybe I write it down. It's the x over r. The x is also 2, the r also 2. 2 radical 2, which implies to be this. Now, tangent 45 degrees is 2 over 2, the y over x, which is 1. So notice that these are in agreement to our result in section 2.1. Okay. Now, notice that the benefit of this definition 1 is you can now use an angle that is more than 90 degrees. Okay, or how about 90 degrees first? Let's do 90 degrees first. Okay, let's call this example 2b. Okay, let theta equals to 90 degrees. Notice that you cannot have a right triangle with right angle at C and also right angle at A. No, you can't. You can't. In other words, you cannot have a right triangle. Okay, I try to picture that for you. Where this is 90 degrees and this is also 90 degrees. It's impossible. It's impossible. Okay. Notice that we cannot using this definition 2, right triangle, to find the value of sine 90 degrees, for example. Okay. However, we can use this definition, the current one, to find the value of sine 90 degrees. Okay. So this is 90 degrees, right? This is 90 degrees. So let's pick a point here. Let's pick a point there. That's a y-intercept. So I can use 0,1. Is it right? Okay, so x equals to 0, the y equals to 1. You use Pythagorean theorem, you will see, well, I mean, from the picture, you see the distance of that coordinate from origin is just 1. So what is sine 90 degrees? Sine 90 degrees is y over r, which is 1. Cosine 90 degrees is x over r, which is 0. Tangent 90 degrees is y over x, which is undefined. Right? Okay, and then from here, of course, we can find the secondary trig values for 90 degrees, like secant 90 degrees is the reciprocal of 0. That's 1 over 0. That's undefined. Cosecant 90 degrees is reciprocal of sine. That's just 1. And cotangent 90 degrees, reciprocal of, in this case, it will be x over r. That's just 0. Okay. Now you should try when theta equals to 0 degrees. Okay. So 0 degrees means you can choose a point on the positive x-axis and find the sine, cosine, tangent of 0 degrees. Okay. Now, once you're done with this example 2b, we can actually do, we can actually update our picture. I think I should say our, what's that? The list of the special trig values for special angles. Now, instead of only 30 degrees, 45 degrees, 60 degrees that we have earlier for sine, cosine, and tangent, right? Now we can add 0 degrees and 90 degrees. Okay? We already have the 30 degrees one. Let's fill it up. So this is 1/2, right? Sine 45 degrees, 1 over radical 2 or radical 2 over 2. And sine 60 degrees radical 3 over 2, right? Now you will see that sine 90 degree is 1 from example 2b. Okay, and sine 0 degree, if you do this guy here, if you do this guy here, then you will see sine 0 degree is simply 0. Okay, now also from what we remember last time, cosine 30 degrees is radical 3 over 2. Okay, cosine 45 degree is 1 over radical 2, which is radical 2 over 2. And cosine 30 degrees is 1/2. Now, another way to memorize this is the cofunction, right? Sine 30 degrees is the same to cosine of the complementary angles, cosine 60 degrees. Okay, remember the cofunction theorem? Okay, right? As long as the angles are complementary, then the values must be, then sine of the one angle is equals to cosine of the other angle. Now, cosine 0 degrees is 1, cosine 90 degrees is 0. Okay. Now, how about tangent? Tangent 30 degrees is 1 over radical 3, which is radical 3 over 3. Tangent 45 degrees 1, tangent 60 degrees radical 3. Tangent 90 degrees, as we have seen above, it's undefined. Okay, while tangent 0 degrees, you will see that's equal to 0. Okay, now I need you to memorize this. Okay, memorize this. You already memorized this part, supposed to be at this point. You already memorized the one in the middle. Okay, now add these two special angles. Memorize. The faster you memorize this, the more likely you are successful in this class. Okay, now let's go on. Let's go on. Example 3. Suppose we have, this one is a bit difficult. Suppose we have the value instead, sine theta is -5 over 13. Okay, where theta is in quadrant 3. Find the remaining 3 values. Find the remaining three values. Okay, the remaining 3 values. I think 3 functions for angle theta. I should say functions instead of values. Okay, now let's try to picture this first. Let's try to picture this first. I mean, seriously, picture that solution. We know sine theta is, in this case, is -5 over 13, right? Which is our y over r. Okay, so call that y over r. So we can assign y equals to -5 and r equals to 13. Notice that r is the distance from origin to that coordinate, right? So r always positive. Now we know this theta is in quadrant 3. So imagine you have a coordinate in quadrant 3, okay, in quadrant 3, and the y is -5. But it has to be in quadrant 3. Okay, this is the theta. Now, can you tell what's the x then? If the r is 13. Now you use Pythagorean theorem. Okay, you use Pythagorean theorem. Let's do it. So x squared plus y squared equals to r squared. X squared plus negative 5 squared equals to 13 squared. You will see in the bang the boom, x squared equals to 144. X, therefore, is plus minus 12, right? And now, since theta is in quadrant 3, then the x must be negative 12, not positive 12. Okay? X is negative 12. Now, that's what we need to go on with, for example, cosine theta then. Cosine theta equals to, now once we get that negative 12, then you fill it in there. Okay, cosine is x over r. Tangent is y over x. Now simplifies this to be 5, positive 5 over 12. Okay, secant theta, reciprocal of cosine, is 13 over negative 12. Cosecant theta is negative 13 over 5. And for tangent theta equals to 12 over 5. Just like that. Yeah. Okay, just like that. Now, suggested homework from here is section 1.3, then number 1 to number 19, and then number 27 to number 55. Okay, now, once you finish study this part, I strongly recommend you to try to watch. So after you're done with this lecture 3 here, section 1.3, 1.4, 1.5, I suggest you to watch the supplemental lecture 3, okay, where I do problems from 1.3, 1.4, 1.5. Okay, then after that, you do the remaining suggested homeworks. So you will see that in my supplemental lecture video, I will do some problems from from the suggested homework here. Not all of them, only some of them. Okay, you see that if we just use our class time in which I do these lecture videos, we can only go through the theory and some examples, right? But we cannot be quite comprehensive in the problems that we do from the book. Okay, now this is for section 1.3. Let's go on to section 1.4. In section 1.4, we will talk about basic identities. There are a lot of identities in trigonometry that you need to memorize. Now, you will see 4 groups of basic identities that you need to memorize as soon as possible. Okay, so beside that, trig values for 30 degrees, 45 degrees, 60 degrees, 0 degrees, 90 degrees, you also need to now memorize these basic identities. There are 4 basic identities you need to memorize. Let me list them first. B1, basic identity group 1, is on ratio and reciprocal. Basic identity 2 is Pythagorean identity. Basic identity 3 is on co-function identities. This is basically the co-function theorems. Okay, and basic identity for negative angle, which I will just list later on, but we will not prove. Okay, now I will first write them down and then prove whichever we can prove. So for ratio and reciprocal identities, we know this already. It's that we don't even need to prove that. Okay, the first one is the tangent theta equals to sine theta over cosine theta. Now, cotangent theta is the reciprocal of tangent theta, and therefore we can also see that as cosine theta over sine theta. Okay, now secant theta is the reciprocal of cosine theta, while cosecant theta is the reciprocal of sine theta. Okay, now please remember this relationship between sine, cosine, tangent, secant, cosecant, cotangent. Okay, so you basically see that once we know sine and cosine, you know tangent, for example. Okay, of these 6 trig functions, sine, cosine, tangent, secant, cosecant, cotangent, of these 6, once you know 2 of them, you know all of them. It's like buy 2, get 6 free. Okay, but we start from here. This is where we start. Next, the second group, Pythagorean identity. Now, because we will prove this in order and we will use this a lot, I will name it, I will number it. So the first one, B21, is sine squared theta plus cosine squared theta equals to 1. Sine squared of an angle plus cosine squared of the same angle is equal to 1. Second, tangent squared theta plus 1 equals to secant squared theta. The third one, 1 plus cotangent squared theta equals to cosecant squared theta. Okay, proof. Now, sine squared theta plus cosine squared theta. Okay, I will prove from I will prove this way. Now we know that sine squared theta is y sine squared. I'm sorry, sine theta is y over r by our first definition above from 1.3. Okay, cosine squared theta is x over r being squared. Now this becomes y squared over r squared plus x squared over r squared, which is y squared plus x squared over r squared because they already have common denominator. But at the same time, we know that x squared plus y squared is the same to r squared. Right? That's why we call this Pythagorean theorem, Pythagorean identity. Okay. So that's the proof for B21. Now, how about the proof for B22? We can use similar proof, but I prefer to use what we have had earlier, proof for B22. From B21, we have sine squared theta plus cosine squared theta equals to 1. Now, divide each term by cosine squared theta. Now, because we divide each term by the same value, then of course the equation is well maintained. All right, let's write it down. So what we have is sine squared theta divided by cosine squared theta plus cosine squared theta divided by also cosine squared theta equals to 1 divided by cosine squared theta. So you see that I divide each term by cosine squared theta, right? And because I divide each term by the same expression, then the quotient should be still equal to each other. However, the first term becomes tangent squared theta. The second term is 1, and the last term is secant squared theta. Okay. Now that's the proof for B22, the second Pythagorean identity. Now the third Pythagorean identity, we prove that here. Okay, the proof for B23, we start from the same from B21. Sine squared theta plus cosine squared theta equals to 1. Now, but this time we divide each term by sine squared theta instead. So we get sine squared theta divided by sine squared theta. We know that this later on becomes 1 plus cosine squared theta divided by sine squared theta equals to 1 divided by sine squared theta. Oops. Divided by sine squared theta. So notice that the first term becomes 1, the second term becomes cotangent squared theta equals to cosecant squared theta. Okay, now this is the second group that you need to memorize. Okay. Okay, the third group. Okay, the third group. B3, the co-function identity. Let angle A and B be complementary angles. In other words, A plus B equals to 90 degrees. They form a right angle. Okay, so the first one, sine of one angle equals to the cosine of the complementary angle. Tangent of one angle equals to cotangent of the complementary angle. Secant of one angle equals to the cosecant of the complementary angles. Okay, now the proof can easily be seen by looking at a right triangle. A right triangle with right angle at C. Let's say this is angle A and this is angle B. Okay, so the opposite uh, sides of angle A is lowercase a, this is lowercase b, this is lowercase c. Now, notice that sine A is equal to A over C. But notice that this A over C is actually also cosine of B, right? From the same triangle. Because what? A and B are complementary, right? So you can put them on the non-right angles of a right triangle. Tangent A is A over B, but notice that A over B is actually cotangent B. Secant A is C over B, which is cosecant of angle B. Okay, therefore we prove that identity. Now, even though I just use a right triangle, this definition still extended and well maintained. These identities are extended and still well maintained, even if we use the first definition, the one in coordinate system. Okay. Now, this co-function identity can also be written in another version. Instead of saying that A and B are complementary, we can say it this way actually. Sine A equals to cosine of 90 degrees minus A. Tangent A is cotangent of 90 degrees minus A. Secant A is cosecant of 90 degrees minus A. Okay. Next identity, next group, if negative angle identities. I will not prove this until we start chapter 3, but since this is one of the basic, one of the group for basic identities, I just give it to you now and start memorizing it. Okay, the first one, sine of negative theta equals to negative of sine theta. Cosine of negative theta equals to cosine theta. Now, if you take college algebra or pre-calculus, you will see that sine is said to have to be an odd function. So if you have an odd function, is sine of negative equals to negative sine. Okay, cosine is said to be an even function, which means cosine of negative equals to cosine of its positive. Okay, now tangent is an odd function. So tangent negative theta is negative tangent theta. We will prove this. We'll prove this after section 3.1. For now, we take it by faith. We will not use this anyway. We will use that later. Okay, but since this is one of the basic identities that you need to memorize, I just give it to you now to memorize that. Consequently, and you will see that secant negative theta is secant theta, because this is the reciprocal of cosine. Okay, cosecant negative theta is negative cosecant theta. cotangent negative theta is negative cotangent theta. For the consequent part, before number 4, 5, 6, the last three that we talked about just now, you don't need to memorize. You don't need to memorize at all. But eventually you will see that it is in your subconscious. Okay. Now, these are the identities. How do we use these? Let's learn some basic use of these identities. I will pick questions from our textbook. Let me start with the following. Number 10. Number 10, if cosine theta equals to radical 3 over 2, then what is the value of secant theta? Now, notice that secant theta is the reciprocal of cosine theta, right? Okay. Now, we know cosine theta is radical 3 over 2. So secant theta is the reciprocal of that. That's 2 over radical 3. I just flipped that upside down. But the problem with this is we have radical on the denominator, which we don't like. So we rationalize, multiply the top and the bottom by radical 3. Okay, that's for number 10. Number 14. I think I can do it here. Save some space. Number 14. We have cotangent theta equals to negative b, where b is not 0. So what will tangent theta be? Tangent theta is 1 over the reciprocal of cotangent, right? Okay. Which is 1 over negative b. Oh, actually, that's it. That's all we need. Right? Number 16. Number 16, we have sine theta equals to 2 over radical 5 and cosine theta equals to 1 over radical 5. What is tangent theta? Tangent theta is using sine and cosine, right? This is the ratio, which is 2 over radical 5 over 1 over radical 5. Now, how do we simplify these complex fractions? What you can do is, you can see this way. You can see this as 2 over radical 5 divided by 1 over radical 5. Okay, 2 over radical 5 divided by 1 over radical 5, multiplied by the reciprocal, cancel the radical 5, you get 2. Okay, there's actually another way to do this, to simplify this fractional, these complex fractions here. Let me show you. 2 over radical 5 divided by 1 over radical 5. We multiply the top and the bottom by the LCD radical 5 over radical 5. Why times? Well, actually, I just multiply by 1, right? Radical 5 over radical 5 is just 1. So I'm not changing the value here. I'm multiplying by 1. However, that 1 is rewritten as radical 5 over radical 5, such that when I multiply this, that will give me 2. And when I multiply this, notice that the radical 5 cancels. That will give me 1. Okay. Now, of course, then this has something to do with your pre-algebra. I taught this in my pre-algebra class. You can also do it that way. That's basically what I say. That's for number 16. Number 20. Number 20, cosine theta equals to 1/3. Now, what does cosine squared theta mean? Well, cosine squared theta is cosine theta being squared. I mean, the value of the cosine is the one being squared. Okay? So cosine squared theta is that 1/3 being squared. That is 1/9. Okay, that's for our number 20. Number 28. Number 28. Now this one is fun. Number 28. Cosine theta equals to 5/13. Theta in quadrant 1. Find sine theta. Now, in the context of this section, I will use the identity. Okay, so solution, first way, by identity that we learned above. What relates sine and cosine? That's actually identity B22. I'm sorry, B21. B21, let's take a look. This is B21. This relates sine and cosine. Okay. I will use that to solve. So sine squared theta plus cosine squared theta equals to 1. Sine squared theta plus 5/13 squared equals to 1. So sine squared theta plus 5 squared over 13 squared equals to 1. So sine squared theta is 1 minus 5 squared over 13 squared. Now you will see we do the LCD, right? 13 squared minus 5 squared over 13 squared. And you will get sine squared theta equals to 144/13 squared, right? So sine theta, if I apply square root property, now sine theta will be the plus minus square root of this, right? Which is plus minus 12/13. Okay, now then from here we adjust. Either sine theta equals to 12/13 or sine theta equals to negative 12/13, right? Now, the problem is theta is in quadrant 1. Theta is in quadrant 1. So you will see the sign, which is y over r, the y is positive, r is positive, right? So the sign is positive. So sine theta will be the 12/13 one, not the negative 12/13. Now, this is the first solution if we use identity. Now, I would like to remind you that we can have the second way. The second way is by seeing it this way: cosine theta equals to 5/13, which is our x over r, right? Okay, now then you picture that on the coordinate system, 5,13. So the x is 5, the y is unknown, the r is 13. By Pythagorean triple, you will see y equals to 12. Remember, this is in quadrant 1, right? So the y has to be positive. Okay, now then sine theta will then be y over r. I think this is a lot faster. Okay. Now, the reason it is a lot faster because we actually have better intuition from the graph. Okay. If you ask me, Thomas, how will you do this problem in the test? I will use method B, the second one. They don't tell us which method to use anyway, right? Okay. Now that's for number 28. Let me continue. Number 36. Number 36, we have cosine theta equals to -1 over square root of 10, while theta is in quadrant 3. Find sine theta. Oh, very similar question then. Oh, find sine theta. Let me use method B first. Method B first. So cosine theta equals to the x over the r. This is my x, this is my r. Okay, so you can assign, okay, x equals to -1, r equals to radical 10. Now then use Pythagorean theorem, x squared plus y squared equals to r squared. That's -1 squared plus y squared equals to radical 10 being squared. That's 1 plus y squared equals to 10. Y squared equals to 9. Y equals to plus minus 3. Okay, so either y equals to 3 or y equals to -3. Now, since theta is in quadrant 3, then the y is negative then, right? Imagine every coordinate in quadrant 3, the y is negative. Therefore, y equals to -3. Okay. Now then, what is the sign? Sine theta equals to y over r, which is -3 over square root. Okay, that's easier, right? Now notice that we have similar questions earlier compared if you see number 28. What makes our solution B in number 28 faster? It is faster because we happen to get a Pythagorean triple, which is not the case for number 36. Now, number 36, we don't have a Pythagorean triple such that we need to compute these ourselves. Right? Okay. Now, the second reason we can do number 28 faster is because the fact that theta is in quadrant 1. So x and y must be positive, no question about it. Right? Okay. While here, when we apply Pythagorean theorem, okay, we get two possible values for y. Until we tell ourselves again, oh, the angle has to be in quadrant 3, therefore the y has to be negative. Okay, now I hope then from there you see what makes this question number 36 a bit more complicated compared to number 28. Next one, number 42. Number 42, find secant theta if tangent theta is 7 over 24 and cosine theta is negative. Okay, solutions. What relates secant theta and tangent theta? By Pythagorean identity, the second formula. tangent square theta plus 1 equals to secant square theta. That's why you need to memorize those identities. Okay, if you don't memorize those, you need to look back into your cheat sheet again. Okay, and you don't even realize which one. It will slow you down so much. And I hate to say this, but a lot of things in trigonometry, you need to memorize first, and then you understand. Now you may say, Thomas, as long as I understand, I will memorize it. Unfortunately, that's not true. Unfortunately, it's not true. In the sense that you will never memorize it if you don't try that first. Okay, so try to memorize that first and then see the reasoning behind that. Now, the reason I want you to memorize these identities because we use them a lot. Okay, that's how important it is. Okay, now let's plug this in. So 7 over 24 squared plus 1 equals to secant square theta. Okay, so we get 7 squared over 24 squared plus, let me do LCD right away. Okay, 7 squared is 49. 24 squared is 576 over 24 squared. That's secant square theta. That's 625 over 24 squared. So when I apply square root property, secant theta equals to plus minus square root of 625 over 24 squared. Don't forget the plus minus. So secant theta equals to plus minus 25 over 24. Okay, now since cosine theta is negative, that implies the reciprocal secant theta is also negative. Is that right? Okay, now we have two possible answers there. We choose the negative one. So secant theta is negative 25 over 24. Okay, now that's for number 42. Next one, number 46. Number 46, we have cosine theta equals to negative 1/3. Theta is not in quadrant 3. Oh, this one. Oh, I'm sorry. Theta is not in quadrant 2. Let's see. Let's see. Solution. We know that cosine theta is negative 1/3. That's x over r, right? So the x is, we can assign x to be negative 1. The r equals to 3. Now, x is negative only in quadrant 2 and quadrant 3. Think about that. Okay, x is negative only in quadrant 2 or quadrant 3. If it says not in quadrant 2, then x, the theta must be in quadrant 3. Right? Now, why do we need that information? Because when we use Pythagorean theorem, we will need to find the y, right? We need to find the y. But later on, you will see the y may be positive, may be negative. Now, how do we decide then if it is positive or negative? Well, by looking at the quadrant. Okay, so y equals to plus minus square root of 8, which is plus minus 2 radical 2. Now, since theta not in quadrant 2, but the cosine theta is negative, right? Then theta must be in quadrant 3. Then the y has to be negative, right? So of those two possible y's, we use the negative. Actually, that's all you need. Actually, that's all you need. Why? Because once you get the cosine theta, then the sine theta will be the y over r. Okay, tangent theta will be the y over x, which is 2 radical 2. Okay, secant theta is actually the easiest one. Secant theta is the reciprocal of cosine, right? Negative 3. Cosecant theta is the reciprocal of sine. That's 3 over negative 2 radical 2. Rationalize the denominator, negative 3 radical 2 over 4. And cotangent theta is the reciprocal of tangent. That's 1 over 2 radical 2, which is radical 2 over 4. Okay, now notice that we just get the rest right away once we know what the y is. Okay, that's for number 46. Lastly, number 52. Let's see what is question number 52. It says here secant theta equals to negative 4. And theta is in quadrant 2. Well, solution. Well, the reciprocal cosine theta must be negative 1/4. Just the reciprocal, right? Okay. And also we know that cosine theta is x over r. So we can assign x to be negative 1, the r equals to 4 by Pythagorean theorem. To the bottom with the boom, you will see the y squared equals to 15. So y equals to plus minus square root of 15, right? Okay. But because theta is in quadrant 2, then the y is positive, right? In quadrant 2, the y is positive. Any point in quadrant 2, the y is positive. Okay. Therefore, the y here is square root of 15. Now, again, once we get the x and the y and the r, we have all trig functions already, right? Sine theta will be the y over r. Cosine theta is known. Tangent theta is the y over r. I'm sorry, the y over x. That's negative square root of 15. Okay. The secant theta is known. Cosecant theta is the reciprocal of sine is 4 over square root of 15. That's 4 square root of 15 over 15. While cotangent theta is the reciprocal of tangent. That's negative 1 over square root of 15. That's negative square root of 15 over 15. Okay, now this is for our section 1.4, the basic identities. Oops, sorry, where's that? Basic identities. Okay, with some examples here. Okay, with some examples here. Your suggested homework will be from this section 1.4, from number 1 to number 53. Okay. Now let's continue with section 1.5. Now, section 1.5 is the continuation from 1.4. The title is More on Identities. However, in this section, we will focus more on the algebraic manipulation. Okay, example one, I will do problems from our textbook. Give me a second, I will take some screenshot from our section 1.5. Example number one, write tangent theta in terms of sine. Now, notice that here, actually there is no basic identities that relates tangent and sine directly. Okay, what we can do, however, is let's rewrite tangent in terms of sine and something else first. So for example, tangent theta, we know tangent theta is sine theta over cosine theta, right? Now, what we can do next is now write cosine theta in terms of sine. Now, we know that sine squared theta plus B21. I hope you remember that. Sine squared theta plus cosine squared theta equals to 1. So cosine squared theta is 1 minus sine squared theta. So cosine theta is plus minus square root of 1 minus sine squared theta. Depends on which quadrant the theta located. But for now, because we don't have the quadrant for theta, now we will just write the cosine that way. So tangent theta is sine theta over plus or minus square root of 1 minus sine squared theta. Okay, now that's for our example 1. Example 2. Write secant tangent theta in terms of sine and cosine, and then simplify. Enlarge this a little bit. Solution. We start with secant theta, tangent theta. Now we will rewrite that in terms of sine and cosine. So this is secant theta is 1 over cosine theta. Tangent theta is sine theta over cosine theta. Isn't it? Now simplify. Basically we multiply that. That's sine theta over cosine squared theta. Okay. Example 3. Add 1 over sine theta plus 1 over cosine theta. Solution. Now to add two fractions, we need LCD, right? So 1 over sine theta plus 1 over cosine theta. I need LCD. So the LCD is sine theta cosine theta. Right? Now, for the first fraction, we already have sine theta. I need to multiply by cosine theta. Top and the bottom, right? Likewise, the second fraction, we already have cosine theta. We need to multiply by sine theta. Now, the reason we need to have LCD is so that we can put them together under one fraction. Cosine theta plus sine theta over the common denominator, sine theta cosine theta. Okay. Example 4. Multiply sine theta plus 2 and sine theta plus minus 5. I hope you remember we're basically going to do foiling here. Solution. We FOIL that. Okay, the first times the first is sine theta. Maybe I write down the question for sine theta plus 2, sine theta minus 5. So first times first, give us sine theta times sine theta, that's sine squared theta. And then FOIL, right? The outers, sine theta times minus 5 is -5 sine theta. The inner 2 times sine theta, that's 2 sine theta. I'm sorry, 2 times -5 is -10. Now combine like terms in the middle, you get sine squared theta minus 3 sine theta minus 10. That's for example 4. Example 5. Substitute x by 3 tangent theta in square root of x squared plus 9. Now, actually, we will do this magic here, especially once we get to calculus 2. Then simplify. Right now, we just do the algebra without knowing why we need to do this, okay? But when we have square root of x squared plus 9 and we replace the x by 3 tangent theta, right? So the x now becomes 3 tangent theta, right? Now simplify. 3 tangent theta being squared, 3 squared is 9, tangent theta being squared is tangent squared theta plus 9. Now notice that we have common factor 9, which I can factor inside the square root. So I get 9 times tangent squared theta plus 1. Okay, I factor the 9, right? Okay, now but tangent squared theta plus 1 is secant squared. Then when we apply the square root, we will get square root of 9 is 3. Square root of secant squared theta is secant theta. Okay, but the square root of any expression should be positive. Now to avoid, but at the same time, secant may be negative. To avoid that from being negative, we apply the absolute value. Okay, actually, it's because of the following principle. Square root of x squared is not x, it's actually absolute of x. Okay, because square root have always positive. Okay, that's the property that I actually use. Now, example 6, proving. Prove that cosine theta times tangent theta equals to sine theta. Now, from now on, when I ask you to prove, you need to do the proving in the following way. Okay, you will do the proving in the following way. First, we need to show the direction of your proof. Most of the time, we will prove from more complicated side to the simpler side. So like in this case, this is more complicated. The left-hand side is more complicated. Okay, the right-hand side seems to be simpler, right? So we will come from left-hand side, proving to right-hand side. Okay, that's what we're gonna do. Now, if that's what you do, then the solution will start with a notation where you start and which direction you go to. So we will prove from left to right. Okay, we will prove from left to right. Left hand side, write this first, equals to cosine theta, tangent theta. Write that first. Whatever you have on the left hand side, you copy paste that thing. Okay, so what you write here has to be exactly the same to what you have on the left hand side there. Okay, now then in the next step, which you will write in the next line, okay, you show what you do to that cosine theta, tangent theta, and manipulate that. Or in this case, I will rewrite the tangent as sine theta over cosine theta. And notice that the sine theta cancels, right? So we get only sine theta, which is what we have on the right-hand side. Okay, so remember, we start from the left-hand side, write that LHS, left-hand side, okay, and then copy down what you have on that left-hand side, in this case, the yellow part. You copy that as is, don't do any computation, don't do any modification. Now, your next step is where you start doing the manipulation. In this case, I rewrite the tangent theta as sine over cosine. And manipulate further, then you show that it is equals to the right-hand side. The end of the proof, we use this box here. It's a square that you fill up. Okay, in math, especially in the last 15, 20 years, that is the notation we use to say that we are now at the end of our proof. Okay, now when you do proofing, you will do it in this structure. Let's do more. Example 7. The proof that sine theta plus cosine theta quantity squared equals to 1 plus 2 sine theta cosine theta. Okay, we will prove from a more complicated side. In this case, from left-hand side, we will prove to the right-hand side. Now, if so, then copy down that left-hand side. Left-hand side is the quantity of sine theta plus cosine theta being squared. And then from here, we use this property. I wonder if you remember, let's remember ourselves, a plus b squared equals to a squared plus 2ab plus b squared. If you FOIL that, okay, that's what I use. So in this case, a plus b squared is a squared plus 2ab plus b squared. Okay, and we also notice that sine squared theta plus cosine squared theta, when you add them, it becomes what? It becomes 1, right? Okay, that's by B21 plus whatever we didn't add. But that is what we have on the right-hand side. Therefore, we are done with our proof. Okay. Now, let's do more. I will do 4 more problems from our textbook. And then in our supplemental, in my supplemental video later on, I will do more. Okay. I need you to get used to the pattern though. Like, how do we show proofing? Okay, how do we show proofing? Number 70. I try not to pick a hard question, but at the same time, not too obvious, not too simple. Okay, number 70, proof that cosecant theta times tangent theta over secant theta equals to 1. There's a kind of like a hint in proving trig identities. If you have, basically, if you can't do it directly, if you cannot simplify directly, think about converting those trig functions in terms of sine and cosine. Now here I will prove from left to right because the left hand side clearly more complicated, right? Now the thing is, it's cosecant, tangent, and secant, right? Okay. What we can do is we rewrite them in terms of sine, cosine. So secant theta is 1 over sine theta. Tangent theta is sine theta over cosine theta. Right? Secant theta is 1 over cosine theta. Now notice that on the numerator, however, the sine theta cancels. Right? Okay, the sine theta cancels. You know what? Let me do it this way. So we get 1 over cosine theta big over cosine theta. I'm sorry, big over 1 over cosine theta. But well, this is just the same expression divided each other, right? So it must be equals to 1, which is our right-hand side. Don't forget that you need to close that, compare that with what you have on the right-hand side before you close the proof. Okay, that's for number 70. Let me do it, the next one, number 78, in the next line here instead of next to it. So this one is a bit longer. Proof number 78, proof that secant theta times cotangent theta minus sine theta equals to cosine squared theta over sine theta. The left-hand side is more complicated, huh? So let's start from the left-hand side. Proof of, I will prove from left to right. Copy the left-hand side first. No modification, don't modify anything. Just write it as is. So that's where we start. And then again, we change that into sine, cosine. If there's no simplification, direct simplification we can do fast, then you change it into sine, cosine. The first term, you see the cosine theta cancels, so I get 1 over sine theta subtracted by sine theta, right? Now then to subtract this, because we have fraction, we do LCD. The LCD is sine theta. So for the second term, if the denominator is sine theta, the numerator, think of it this way. This is over 1, right? So if the denominator multiplied by sine theta, the numerator you multiply by another sine theta. Okay, so we end up with sine squared theta, which is, once we have LCD, we have 1 minus sine squared theta on the numerator over sine theta. However, 1 minus sine squared theta is cosine squared theta, right? Which is our right-hand side now, and therefore we are done with the proof. Okay. Number 86. Oh no, number 86 is basically what we did earlier. Number 90. Number 90. Number 90, proof that cosine theta times cosecant theta plus tangent theta equals to cotangent theta plus sine. Proof from left-hand side to right-hand side. Now, if you think it will go too far to the left, you can write that left-hand side, copy the expression of left-hand side in the next line. Okay, cosecant theta plus tangent. Just keep in mind, the next step you do should be written in the next line. Okay, so what I will do next is to rewrite that cosecant theta as 1 over sine theta and tangent theta as sine theta over cosine theta. Okay, so cosine theta being distributed, we will get cosine theta over sine theta for the first term. For the second term, however, cosine theta times sine theta, cosine theta cancel, we get only sine theta. Now, cosine over sine, however, is cotangent theta. Now you see that we match the right-hand side, which is the end of our proof. Okay, and that's it for this section 1.5. Don't forget, after this, when you have a chance, try to watch the supplemental lecture video. Okay, so long.